Hello engineers, welcome to 16th lecture of ASME BPVC section 8 Division 1 code training. Today we will discuss about UG28 clause, that is thickness of shells and tubes under external pressure. Today we will derive the thickness of thickness calculations for external pressure. Okay, so before going to derive that, so let's see some common questions why we need to calculate this thickness for under external pressure. So why we need to calculate for external pressure? Anyway, our internal pressure is greater than external pressure, right? Most of the cases. So we need to, if we calculate thickness calculations for internal pressure, it will withstand the external pressure also, na? So why we need to calculate, especially for external pressure? Anyway, our external pressure is atmospheric pressure, most of the cases. But why we are calculating the pressure here, thickness here? So the reason behind this is to avoid buckling failure, guys. In engineering, we already studied about buckling failure. Even if we apply a small amount of load, so buckling will happen, right? So that's why to avoid this buckling failure, so we are calculating the thickness for external pressure case also. So next question is, what is the difference between failure due to internal pressure and external pressure? What is the failure mode in internal pressure, guys? So in internal pressure, we see if we apply a pressure, so it will try, the material try to expand. That means yielding will happen. After that, failure will happen, right? So first yielding takes place. Yielding is nothing but deformation, right? So deformation takes place, and after that, cracking starts. But in external pressure, there is no yielding, guys. It will suddenly buckle. So without giving any prior intimation, it within seconds buckling will happen. So due to that, most of the engineers where they are working there, right, in manufacturing unit, so they will suffer due to this buckling. So we need to avoid this buckling failure. So that's why we are mainly calculating this thickness formula. Okay. So when we experience this buckling failure in our vessel, when we experience this buckling failure in our vessel, so let's see that also. So this is the failure due to internal pressure and this is the failure due to external pressure. So if you observe in the image, the buckling will happen. So these failures we cannot predict, guys. This will happen suddenly. Okay. So already I mentioned each and every point what I'm saying in the PPT. So next one is which loads and factors create the buckling. So first, when we experience this buckling failure, third question, I need to answer third question, right? When we experience this buckling failure in our vessel, so when the tank is empty, it is subjected to external pressure, such as vacuum condition during cleaning. We need to ensure that the tank was not buckle under this condition. What is the meaning of this point, guys? So what is the meaning of this point? Okay, anyway, in working condition, our vessel is filled with fluid, right? So in that condition, our internal pressure is the main criteria. But once, if you want to clean our vessel, so we need to empty the tank. In that case, sometimes our pressure, the inside pressure is below the external pressure. It will go up to vacuum conditions also. That means zero pressure, zero pressure conditions also. At that time, the sucking action will happen inside the vessel. So due to that, and also external practicing and outside of the vessel. So due to these main conditions, the buckling will takes place, guys. So we cannot predict that how much fast buckling will happen. So it is immediate within seconds the tank will be buckled. Okay. So to avoid this all the criteria, we need to do thickness of shells under external pressure. There is one more question. Which loads and factors create the buckling? Which loads, guys? So generally, outside pressure is like this only, right? So in all directions, the outside pressure will act on the tank. So what is this loading type? This is compressive loads, right? So in compressive loads only buckling will happen. And what are the factors create buckling? So mainly, if this is our vessel, if this is our vessel, so there are two major factors. There are three major dimensions will create the buckling, guys. One is thickness of the vessel, thickness, thickness. Another one is length, and another third one is diameter of the vessel. So these three dimensions will play major role in buckling. So there is a we already studied in engineering, right? So L by D ratio, D naught by T ratio, nothing but slenderness ratio. Slenderness ratio. I hope you already uh, listened this word in previously. I think in engineering SYM, I think strength of materials, you already calculated this slenderness ratio. That is L by D ratio, L by D ratio, or D by T ratios. So already I think these two ratios are nothing but slenderness ratio. These two ratios create the buckling, guys. So we need to take care of that one. And the next one is, so what we need to do to avoid buckling failures. So what we need to do, guys, how to prevent this buckling failure under external pressure. So we have three methods. So first one is stiffener rings, guys. So if we add stiffener rings for our outer vessel or in whatever maybe whatever the vessel, so we need to it will provides you additional support to prevent buckling. So stiffener rings means round. If this is your vessel, right? This is your vessel. So stiffener rings like this. So it is round. So it will give additional support to your vessel. So it will try to avoid the buckling failure, guys. So next one is thick walls. We need to increase the wall thickness as much as we can. So we need to increase this thickness, guys. So if we increase the thickness, so it will withstand the buckling pressure, buckling failure. Okay. So next one is design codes. We need to follow proper design codes like ASME BPVC section at Division 1 code. So whatever the other codes also the EN codes. So to calculate this thickness under external pressure, we need to follow these three concepts. We can avoid the buckling failure. I hope you understand this all the basic concepts before going to derive the UG28 thickness formulas. So let's start. Let's continue the session. Mm, So the first, if you go to UG28, you will see the formulas given for cylindrical shells and tubes. So in that also, the formula is divided into two types based upon the slenderness ratio. If cylinders having D by T ratio is greater than 10, then what is the thickness formula for external pressure, under external pressure, right? So let's see the first step. So in first step, assume a value for thickness. Just we are assuming the one thickness value, guys. Anyway, we already calculated thickness for internal pressure by using UG27. We already have UG27 formulas for internal pressure. So if we get T is equal to 10 mm for internal pressure, we can assume the 10 mm here, or you can any assume random value here for calculation purpose. So engineering means assumptions, right? So we need to assume some dimensions. We need to fulfill our criteria. So determine the L by D and D naught by T ratios. So these ratios I already told you, slenderness ratio. Based upon the slenderness ratios only, we can define the buckling pressure or buckling failure. This after determining the slenderness ratios, so find factor A. So from where you need to find factor A? So refer ASME section 2 part D sub part 3 figure G, guys. So if you open that, so if you see like this in sub part 3 figure G figure, this is the figure G figure. You can see L by D ratio here. This is factor A values. This is the factor A values. This is the D naught by T ratios. We already have L by D and D naught by T ratios. So if you draw, for example, if L by D is 10 and the D naught by T is 20, here is the 20 line, right? So this is the 20 line. If you draw a line vertically downwards, so somewhat here, so your factor A value is 0.003. This is your factor A values. So like that you need to find. If your L by D ratio is greater than 50, up to 50 only the graph given. If the greater than 50 you got, if you got to greater than 50, then you need to select 50 only. You need to select 50 only. If below 1.2, you need to select 1.2 only. So this is the conditions given in the code, guys. So let's move to next step. The next step is after finding uh, a factor A value, we need to go to table 1A of subpart 1 in section 2 part D. If you go to section ASME BPVC section 2 part D, that is table 1A 1B, you will get some stress values there. So, and also you will get some charts, external pressure charts. So for different materials, there are different external pressure charts given in that table 1A. So if you see here, I'm selling carbon steel value, which is say 36. For this 36, if you go to next slide, so this is the 19th one, right? So same 19th one you will got minimum tensile strength, yield strength, and also external pressure chart to find out factor B. So from here we will find the factor B values, guys. So let's see what is how CS2 chart looks like. So this is the CS2 chart, okay? So from this chart, we already know factor A values. So that is 0.003, somewhat here. So for our material, we already know Young's modulus. For example, if you take Young's modulus is 29 point something. This is, so if you draw a vertical line, so if you draw a horizontal line, here is the matching line, right? So 16,000 is our factor B value. Okay. So like that, we need to find, you need to find factor A and factor B values, guys. If if your A falls in here, so left side of the table, so what you need to do? So that will also I will tell you. Just remember this point. So next one is after finding the factor B value, we will calculate the maximum allowable external working pressure. So this is the figure I'm showing you for your reference purpose. This is the length, this is the D naught, and this is the thickness. So these are the general dimensions, right? So let's find the maximum allowable external working pressure. It denotes as PA. So PA equal to 4B by 3 into D naught by T. We already find out the D naught by T. We already know B value, that is 16,000. So it is easy to calculate PA right now. So this is how we need to calculate maximum allowable external pressure. Okay. So B is the factor, D naught is the outside diameter, T is the thickness. Next one, I already told you, if factor A falls into left side of the table, then what we need to do, guys? So if factor A falls into left side of our table, so the code given direct formula by using the factor A. So P is equal to 2AE by 3 into D naught by T. So A is the factor from where we get figure G, right? E is the Young's modulus, L is the total length of the shell or length between the line of supports. I already shown you previous diagram, right? So like that we need to find out the maximum allowable working pressure. So after finding the external pressure, so compare the PA value with with our design pressure. P is our design pressure, PA is our maximum allowable external pressure. If PA is if PA is smaller than P, select the larger value for 3. We need to increase the T values. Need to increase the T value. We need to increase the T value, thickness value. Previously we took 10 mm, right? So we need to try with next 12 mm. So like that we need to do up to where? So PA up to PA is greater than P. Then only our calculation is satisfied. Otherwise, it will rejected by the inspection specialist. Okay. So I already told you for L by D ratio is greater than 50, we need to select L by D is equal to 50, right? And for values L by D is less than 0.05, then we need to choose 0.05 only. So that is all about if D naught by T ratio is greater than or equal to 10 mm. So let's see next one. So if D naught by D ratio is less than 10, what we need to do? So like by using the same process only, we will find factor A and factor B values. Okay. So if D naught by T ratio is less than 4, then what is the value of factor A? So our chart gives D naught by T is greater than or equal to 4, right? But if D naught by T less than 4, then how to calculate A value means the code given one formula. A is equal to 1.1 divided by D naught by T whole square. So by using this formula, we will find the factor A value. After finding the factor A value, we will find the factor B values. Okay, I hope this is clear. So by using factor A value and factor B value, we will find the maximum allowable external working pressure by using these two formulas, guys. So for this condition, the ASME code given that two formulas. We need to satisfy these two formulas. Okay. So after that, here S is the minimum of twice the maximum allowable stress and 0.9 percentage of yield stress. And next one is whatever the maximum allowable external pressure, which is smaller. So we will select that. If P is equal to, if PA1 is the smaller, we will select this PA1 and we will compare with our design pressure. Okay, PA1 with design pressure. If whatever the small value, we will choose that one. So and that after choosing that, we will compare with our design pressure. So if PA is more smaller, then we need to increase the thickness again. Okay, so like that we need to do until PA is greater than P. Why PA is greater than P, guys? Why PA must be greater than P? This is the allowable pressure. This is our design pressure. The allowable pressure for material, the allowable pressure for material must be greater than the design pressure. Then only it will withstand this pressure, right? If this is 100, this is 50, 75, then only it will withstand, the material withstand this 75 pressure. If this is 75 and this is 100, how will our material withstand our design pressure, right? So I hope you understand this point. So that's why our PA must be greater than P. Okay. I hope you understand the content. If you like my content, please share to your friends also, guys. So they will also get benefited. Please, please subscribe and support me. So many members are watching, but they are not subscribing my channel. So please try to subscribe my channel. So it will boost me personally. So thank you, guys. Jai Hind.